Imagine you are sending a series of postcards to a friend. Each postcard has a picture, the data, and a little note on the back, the control information. If you just put the postcards in a bag without any way to tell where one ends and the next begins, your friend might read two pictures together and think they are one big picture. In computer networks, the data link layer does the same job. It packages raw bits into frames so the receiver knows exactly where each piece of data starts and stops. This framing is necessary because the layer below the physical medium only sees a long stream of zeros and ones, just like an endless string of beads. Without frames, the receiver cannot separate one message from another, cannot detect missing or extra bits, and cannot apply error-checking codes correctly. Therefore, framing is the glue that turns a raw bit soup into understandable packets. Fixed-length byte count framing is like putting a fixed-size envelope on every postcard. Suppose every envelope can hold exactly 10 letters. The first byte of the envelope tells you there are 10 bytes in this frame. The receiver reads that first byte, knows it must read exactly 10 more bytes, and then stops. The next byte after those 10 is the start of the next frame. How it works: the sender adds a length field, usually 1 or 2 bytes, at the beginning of each frame. The length field value equals the number of data bytes that follow. The receiver reads the length field, then reads exactly that many bytes as payload. Analogy: a train of boxes where each box starts with a tag that says this box holds 5 toys. The worker knows to take the next 5 toys and then look for the next tag. Pros: simple to implement, no special marker bits needed. Cons: if a bit in the length field gets flipped, the receiver may read too many or too few bytes, causing loss of synchronization. Example: if the length field is 1 byte, the maximum payload is 255 bytes. A frame that carries 50 bytes of data will be 1 length plus 50 equals 51 bytes long. Flag-based framing uses a special pattern called a flag to mark the start and end of a frame, just like a fence gate that says enter here and exit here. The classic flag used in HDLC and PPP is the 8-bit pattern 01111110, hex 0x7e. Problem: what if the data itself contains the same pattern? The receiver would think the frame ended early. Solution: bit stuffing. Whenever the sender's data contains 5 consecutive ones, it automatically inserts a single 0 after them. This guarantees that the flag pattern, 6 ones surrounded by zeros, never appears inside the data. Step by step: 1. Sender adds flag at the beginning. 2. While scanning data, if it sees 11111, it stuffs a 0, resulting in 111110. 3. After the data, another flag is added. 4. Receiver reads bits, removes any stuffed 0 that follows 5 ones, and then looks for the flag pattern to know where the frame ends. Analogy: think of a story written on a scroll where every time the word end appears inside the story, you write end star, add a star, to tell the reader that this end is not the real end of the story. The real end is always marked by a bold underlined end. Pros: works with any payload length, easy to detect boundaries. Cons: bit stuffing adds extra bits when the data contains many one-runs, slightly reducing efficiency. Byte stuffing, also called character escape, is similar to flag-based framing, but works on whole bytes instead of individual bits. Imagine you are sending a text message where the special character hash means start of a new message. If the actual message itself contains hash, you need a way to tell the receiver this hash is part of the text, not a delimiter. Step 1. Choose a flag byte, for example 0x7e, to mark the start and end of a frame. Step 2. Choose an escape byte, for example 0x7d. Step 3. While sending data, if a byte equals the flag or the escape byte, the sender first sends the escape byte, then the original byte XOR'd with 0x20, a simple transformation. Step 4. Receiver, upon seeing the escape byte, knows to reverse the transformation to retrieve the original byte. An analogy: a mailbox where the word stop means the letter is finished. If you need to write the word stop inside the letter, you first write escape and then stop. The mailbox keeper knows that stop really means the word stop in the text, not the end of the letter. Pros: easy to implement in software byte-oriented systems, for example UART. Cons: if the data contains many flag or escape bytes, the overhead can grow. Each such byte becomes 2 bytes. Synchronization means that the receiver knows exactly where each frame begins and ends. Without proper framing, the receiver could lose track and start interpreting middle-of-frame bits as new messages, leading to garbled data. Most frames end with a checksum or cyclic redundancy check, abbreviated CRC. The receiver computes the checksum over the received payload and compares it with the transmitted value. If the framing is wrong, for example because a length field was corrupted, the receiver will read the wrong number of bytes and the CRC will most likely fail, alerting the system to discard the frame. CRC treats the payload as a block of bits. If the block boundaries shift, the polynomial division will produce a completely different remainder, signaling an error. Therefore, reliable framing is a prerequisite for any error detection scheme. Think of a train where each carriage has a unique barcode. The scanner at the station reads the barcode, frame start, counts the number of seats, payload length, and then verifies the final checksum sticker before letting passengers off. If the train slips lost synchronization, the scanner reads the wrong barcode and the checksum fails. Frames provide synchronization, where to start or stop reading. Frames carry error-detecting codes, CRC checksum, that rely on correct boundaries. A corrupted frame boundary typically results in a CRC mismatch, prompting retransmission. Explanation: throughput is the amount of useful data delivered per unit time. Efficiency measures how much of the transmitted bits are actual payload versus overhead, flags, length fields, stuffing, CRC, etc. Formula: efficiency equals payload size divided by the sum of payload size and overhead, multiplied by 100%. Example 1, fixed length, no stuffing. Payload equals 1000 bytes. Length field equals 2 bytes. CRC equals 4 bytes. Total frame size equals 1000 plus 2 plus 4 equals 1006 bytes. Efficiency equals 1000 divided by 1006, multiplied by 100, approximately 99.4%. Example 2, flag based with bit stuffing. Assume a payload of 1000 bits. In the worst case, every fifth bit is a 1, causing a stuffed 0. This adds roughly 1000 divided by 5 equals 200 extra bits. Flags equal 2 bytes, 16 bits each, total 32 bits. CRC equals 32 bits. Total bits equal 1000 plus 200 plus 32 plus 32 equals 1264 bits. Efficiency equals 1000 divided by 1264, multiplied by 100, approximately 79.1%. Example 3, byte stuffing. Payload equals 500 bytes, of which 20 bytes equal the flag 0x7e or escape 0x7d. Each special byte becomes 2 bytes after stuffing, extra 20 bytes. Flags equal 2 bytes, CRC equals 4 bytes. Total equals 500 plus 20 plus 2 plus 4 equals 526 bytes. Efficiency equals 500 divided by 526, multiplied by 100, approximately 95.1%. These numbers show how the choice of framing directly influences the usable throughput. In high-speed links, even a few percent loss can be large, so designers pick framing methods that keep overhead low for the expected traffic pattern. When picking a framing method, engineers weigh several practical factors. Channel characteristics - if the physical layer transmits bits in a steady clocked stream, for example Ethernet, fixed length or length field framing works well. If the channel is noisy and bits may be dropped, a delimiter that can be ray-detected, flag-based, is safer. Payload variability - applications with highly variable message sizes benefit from length field or flag-based framing, while fixed-size packets, for example ATM cells, can use simple fixed-length frames. Processing overhead - bit stuffing requires bit-level manipulation, which can be costly on low-power microcontrollers. Byte stuffing is cheaper on byte-oriented CPUs. Error propagation - in fixed-length framing, a single-bit error in the length field can misalign many subsequent frames. Flag-based framing limits error propagation because each frame is self-delimiting. Implementation simplicity - fixed length is the simplest to code. Flag-based with stuffing needs extra logic for inserting and removing bits bytes. Throughput needs - if maximum efficiency is critical, for example satellite links, choose the method with the smallest expected overhead for the typical data pattern. Standard compatibility - many protocols are already defined, PPP, HDLC, Ethernet. Using a standard framing method eases interoperability. A decision matrix or checklist based on the above points helps designers select the most appropriate technique for a given scenario. Modern protocols often blend several framing ideas to get the best of each world. PPP point-to-point protocol uses a flag byte 0x7e at both ends and byte stuffing with an escape byte 0x7d. This gives clear delimiters while keeping the implementation byte oriented, suitable for serial links. HDLC, high-level data link control, employs flag-based framing with bit stuffing to guarantee the flag pattern is unique. It also adds a 16 or 32-bit CRC for strong error detection. Ethernet IEEE 802.3 uses a preamble of 7 bytes of 0x55 followed by a start frame delimiter 0xd5 to achieve synchronization, then a length/type field, payload, and a 4-byte frame check sequence. FCS no explicit stuffing because the physical layer encodes data to avoid too many consecutive ones. Wi-Fi IEEE 802.11 starts each frame with a PLCP preamble and header that contain timing and length information, then the M-A-C frame followed by a CRC. The M-A-C layer also may use aggregation, a MSDU, that packs multiple Ethernet-like frames together. USB uses NRZI encoding with bit stuffing, plus packet identifiers that act as delimiters. These hybrid schemes demonstrate that real-world systems combine delimiter flags, length fields, and stuffing, as needed to satisfy synchronization, error detection, and efficiency goals on diverse media.